Hello students, welcome to the lecture on vectors. And after this lecture, we will be able to learn the following objectives. Define the scalars and vectors. Discuss the coordinate systems. Discuss direction ratios and direction cosines. Explain the magnitude and direction of a vector. Let us start with the introduction to vectors. Vectors are introduced as geometric objects, namely as directed line segments or arrows. The operations of addition, subtraction, and multiplication by a scalar, real number, are defined for these directed line segments. The 2- and 3-dimensional rectangular Cartesian coordinate systems and then introduced and used to give an algebraic representation for the directed line segments or vectors. Two new operations on vectors called the dot product and the cross product are introduced. Some familiar theorems from Euclidean geometry are proved using vector methods. Euclidean vector. It is frequently represented by a line segment with a definite direction or graphically as an arrow connecting an initial point A with a terminal point B.
A quantity that has both magnitude and direction is a vector represented by an arrow. The arrow's direction is the direction of the quantity, and the length of the arrow indicates its magnitude. Displacement, velocity, and acceleration are all vectors. In equations, vectors are written in boldface. Ordinary quantities such as time and mass are scalars. In equations, scalars are written in italics. The magnitude of a vector is also a scalar, the same letter, but in italics. With vectors, even the most familiar mathematical operations acquire an entirely new meaning. For example, when two vectors are added together, the sum isn't merely a number, it's a new vector. Also, vectors can be subtracted from each other, and the result is another new vector. A vector can be multiplied by a scalar. This new vector has the same direction if the scalar is positive, but its magnitude can be different. Multiplying a vector by a negative scalar reverses its direction. A vector can be multiplied by another vector. The dot product of A and B is a scalar that measures the tendency of the two vectors to point in the same direction. A dot B is equal to the length of A times the length of B times the cosine of the angle between them. If A and B are perpendicular, their dot product is 0. And the dot product of a vector with itself is just the square of its length. The cross product of two vectors is a new vector, perpendicular to the plane of the two original vectors. Its length is the area of the parallelogram formed by the original vectors. Its direction is determined by the right-hand rule. The cross product measures the tendency of two vectors to be perpendicular, and it's one of the more effective tools for describing, spinning, or rotating objects. Vector algebra makes use of two perpendicular unit vectors, I and j. The little hat over the vector means that it has length 1. The vector from the origin to the point with coordinates x, y is the sum of two perpendicular vectors, a horizontal vector xi and a vertical vector yj. With the help of I and j, adding and multiplying vectors can be accomplished by ordinary algebra. In three-dimensional space, a third unit vector k is used. K is perpendicular to the plane of I and j. A three-dimensional vector is written xi plus yj plus zk.
Let's now discuss about the scalars and vectors. Some physical quantities such as length, area, volume and mass can be completely described by a single real number. Because these quantities are describable by giving only a magnitude, they are called scalars. To distinguish between scalars and vectors, we will denote scalars by lowercase italic type such as A, B, C, etc. and denote vectors by lowercase boldface type such as U, V, W, etc. It is customary to leave scalars as regular handwritten script and modify the symbols used to represent vectors by either underlining such as shown or by placing an arrow above the symbol. Now determine whether a scalar quantity, a vector quantity or neither would be appropriate to describe each of the following situations. The outside temperature is 15 degrees Celsius. A truck is traveling at 60 km per hour. The water is flowing due north at 5 km per hour. The wind is blowing from the south. A vertically upwards force of 10 newtons is applied to a rock. The rock has a mass of 5 kilograms. The box has a volume of 0.25 meter superscript 3. A car is speeding eastward. The rock has a density of 5 gram per centimeter superscript 3. A bulldozer moves the rock eastward 15 meter. The wind is blowing at 20 km per hour from the south. A stone dropped into a pond is sinking at the rate of 30 cm per second. Geometrical representation of vectors. The vectors determined by both a magnitude and a direction. They are represented geometrically in 2 or 3-dimensional space as directed line segments or arrows. The length of the arrow corresponds to the magnitude of the vector, while the direction of the arrow corresponds to the direction of the vector. The tail of the arrow is called the initial point of the vector, while the tip of the arrow is called the terminal point of the vector. If the vector v has the point P as its initial point and the point Q as its terminal point, we will write v equal to vector PQ equal vectors. Two vectors u and v which have the same length and same direction are said to be equal vectors even though they have different initial points and different terminal points. If u and v are equal vectors, we will write u is equal to v. Sum of two vectors. The vector u plus v, which is written as u plus v, is the vector whose initial point is the initial point of u and whose terminal point is the terminal point of v. Negative of a vector. If u is a non-zero vector, we define the negative of u, denoted negative u, to be vector whose magnitude or length is the same as the magnitude or length of the vector u, but whose direction is opposite to that of u. Difference of two vectors. If u and v are any two vectors, we define the difference of u and v, denoted u minus v, to be vector u plus negative v. To construct the vector u minus v, we can either construct the sum of the vector u and the vector negative v, or position u and v so that their initial points coincide, then the vector from the terminal point of v to the terminal point of u is the vector u minus v. Here we will talk about the coordinate systems. Coordinate system is a system which uses one or more numbers or coordinates to uniquely determine the position of a point or other geometric element of a manifold such as Euclidean space. A coordinate system is a frame of reference that is used as a standard for measuring distance and direction. If we are working with vectors in two-dimensional space, we will use a two-dimensional rectangular Cartesian coordinate system. If we are working with vectors in three-dimensional space, the coordinate system that we use is a three-dimensional rectangular Cartesian coordinate system. To understand these two- and three-dimensional rectangular coordinate systems, we first introduced a one-dimensional coordinate system, also known as a real number line. Let R denote the set of all real numbers. Let 1 be a given line. We can set up a one-to-one relationship between the real numbers and R as the points on 1 as follows. Select a point on O, which will be called the origin on the line 1. To this point, we associate the number 0. Select a unit of length and use it to mark off equidistantly placed points on either side of O. The points on one side of O, called the positive side, are assigned the numbers 1, 2, 3, etc., while the points on the other side of O, called the negative side, are assigned the numbers 1, 2, 3, etc. A one-to-one correspondence now exists between all the real numbers R and the points on 1. The resulting line is called a real number line, or more simply, a number line, and the number associated with any given point on the line is called its coordinate. This is a one-dimensional coordinate system. The two-dimensional Cartesian coordinate system has as its frame on reference two number lines and intersect at right angles. The horizontal number line is called the x-axis and the vertical number line is the y-axis. The point of intersection of the two axes is called the origin and is denoted by O. To each point P in two-dimensional space, we associate an ordered pair of real numbers x, y, called the coordinates of the point. The number x is called the x-coordinate of the point and the number y is the y-coordinate of the point. Three-dimensional rectangular Cartesian coordinate system has its frame of reference three number lines that intersect at right angles at a point O called the origin. The number lines are called the x-axis, the y-axis and the z-axis. Right-handed Cartesian coordinate system is a right-handed Cartesian coordinate system is one in which the coordinate axes are so labeled that if we curl the fingers of our right hand so as to point from the positive x-axis towards the positive y-axis, the thumb will point in the direction of the positive z-axis. The dot product, scalar product. The dot product is a method for multiplying two vectors. Because the product of the multiplication is a scalar, the dot product is sometimes referred to as the scalar product. The dot product will be used to find an angle between two vectors and will have an applications in finding distances between points and lines, points and planes, etc. If u equal to u1, u2 and v equal to v1, v2 are two vectors in R2, we define their dot product as shown on screen. If u equal to u1, u2, u3 and v equal to v1, v2, v3 are two vectors in R3, we define their dot product as seen on screen. Distance between a point and a line in R2. To find the distance d between a point P and a line 1 in R2, we select a point Q on the line 1, then the distance d is the length of the projection of OP bar on n, a normal vector to the line 1. The cross product, vector product, we were introduced to the dot product of two vectors. The result of taking the dot product of two vectors is a scalar quantity. We now introduce a second method of multiplying two vectors from R3 that results in a vector quantity. The symbol used to denote this product is a cross, hence the name cross product. Because the result is a vector, the term vector product is sometimes used for this product. The cross product has a number of applications. We will use the cross product to find the areas of triangles and parallelograms. It will also be used to calculate the volume of a parallel pipe and later to find the distance between a point and a line in R3. If U equal to U1, U2 and U3 and V equal to V1, V2, V3 are two vectors in R3, the cross product U cross V is the vector in R3 as seen on the screen. Now we will discuss about direction ratios and direction cosines. Direction ratios provide a convenient way of specifying the direction of a line in three-dimensional space. Direction cosines are the cosines of the angles between a line and a coordinate axis. Consider the point P 4, 5 as its position vector 4i plus 5j is shown at your screen. The direction ratio of the vector OP is defined to be 4:5. We can interpret this as stating that to move in the direction of the line OP, we must move 4 units in the x direction of every 5 units in the y direction. The direction cosines of the vector OP are the cosines of the angles between the vector and each of the axes. Specifically referring to the figure, these are cos alpha and cos beta. Direction ratios and cosines in 3 dimension. Given a vector r is equal to ai plus bj plus ck its direction ratios, r a ratio b ratio c. This means that to move in the direction of the vector, we must move a units in the x direction and b units in the y direction for every c units in the z direction. The direction cosines are the cosines of the angles between the vector and each of the axes. It is conventional to label direction cosines as 1, m and n, and they are shown. Components of a vector. A displacement of 1 unit in the positive x direction is labeled I and a displacement of 1 unit in the positive y direction is labeled j. Because each has the length of 1 unit, they are called unit vectors. Here we will discuss about the magnitude and direction of a vector. Consider the vector AB equal to 2i minus 5j, the magnitude or modulus of vectors represented geometrically by the length of the line AB. Using Pythagoras theorem, vector AB is 5.39 units. Its direction is defined by the angle AB makes with the positive x direction. This angle is minus theta. AB has magnitude 5.39 units and its direction makes an angle minus 68.2 degrees with the x-axis. Adding vectors. Vectors have magnitude and direction. When vectors are added, it is equivalent to one displacement followed by another. Subtracting vectors. This is operating as addition, but in this we will subtract the vectors. Relative position vectors. The position vector of B relative A is simply vector AB, where A and B are the position vectors of A and B respectively relative to the origin O. Equal vectors. If the vectors Ci plus dj and Ei plus fj are equal, then Ci plus dj equal to Ei plus fj, and it follows that C equal E and D equal F. These are the only possible conclusions if the vectors are equal. Vectors in 3 dimensions. In order to work in 3 dimensions, it is necessary to define a third axis OZ so that OX, OY, OZ form a right-handed set as in the diagram opposite. An ordered ratio of numbers such as 2, 3, 4 is necessary to define the coordinates of a point, and a vector must have 3 components. Scalar products. The scalar product of 2 vectors A and B is defined as AB cos theta, where theta is the angle between the 2 vectors, and A and B are the module or magnitude or A and B. The scalar product is usually written as shown, read as a dot b. So a dot b equals to ab cos theta. The scalar product follows both the commutative and distributive laws. Now, in the end, let us summarize what we have learnt in this lecture. Vectors are first introduced as geometric objects, namely as directed line segments or arrows. The 2 and 3-dimensional rectangular Cartesian coordinate systems are then introduced and used to give an algebraic representation for the directed line segments or vectors. The Euclidean vector is frequently represented by a line segment with a definite direction or graphically as an arrow connecting an initial point A with terminal point B. Some physical quantities such as length, area, volume, and mass can be completely described by a single real number. Because these quantities are describable by giving only a magnitude, they are called scalars. The vectors are determined by both a magnitude and a direction. They are represented geometrically in 2 or 3-dimensional space as directed line segments or arrows. The tail of the arrow is called the initial point of the vector, while the tip of the arrow is called the terminal point of the vector. A coordinate system is a frame of reference that is used as a standard for measuring distance and direction. The point of intersection of the two axes is called the origin and is denoted by O. A right-handed Cartesian coordinate system is one in which the coordinate axes are so labeled that if we curl the fingers on our right hand so as to point from the positive x-axis towards the positive y-axis, the thumb will point in the direction of the positive z-axis. Direction ratio provide a convenient way of specifying the direction of a line in 3-dimensional space. Direction cosines are the cosines of the angles between a line and the coordinate axis. The scalar product follows both the commutative and distributive laws.